Bun găsit la emisiunea Știință și Cunoaștere. Astăzi avem un subiect fierbinte într-un anotimp foarte rece, așa că sper să vă încălzească puțin atenția prin noutatea tematicii, precum și a invitatei emisiunii. Vom vorbi despre funcționarea acestui astru care ne oferă căldură, lumină, energie și viață, și anume Soarele. Soarele este astrul fără de care viața pe pământ nu ar fi fost posibilă, dar acest astru are o funcționare pe baza unor legi bine definite, iar activitatea sa variază de la o perioadă de timp la alta. Și totuși, acest astru emite energie a căror intensitate poate fi mai mare sau mai mică, influențând temperatura, astfel că ziua este mai cald, iar noaptea este mai frig. Dacă cerul e acoperit de nord, temperatura este mai mică, dacă cerul este senin, temperatura este mai mare. Deoarece orbita Pământului este ușor eliptică, biosfera beneficiază de 4 anotimpuri. Și totuși, cercetătorii climei rareori acordă atenție influenței Soarelui asupra climei terestre, ei fiind focalizați mai ales pe factorii antropici și eventual alți factori naturali din atmosferă, litosferă și hidrosferă. Altfel spus, oceanele, solul și apele care sunt implicate în marile circuite climatice. Însă o altă categorie de cercetători s-au specializat pe studiul Soarelui, iar aceștia sunt astrofizicienii și matematicienii. Încerc să înțeleg de ce aceste două grupe de cercetători nu reușesc să găsească numitori comuni în vederea obținerii unor rezultate mai bune legate de înțelegerea climei. De ce? Știința climatică ne ajută să ne pregătim din timp pentru diversele scenarii posibile și ne poate ajuta să supraviețuim dacă vreunul din aceste scenarii va deveni real în următoarea perioadă. Invitata emisiunii este matematiciana și astrofiziciana Valentina Zarkova, cercetătoare la Universitatea Northumbria din Marea Britanie. Doamna Zarkova a descoperit o formulă matematică unică în lume, care i-a adus aprecieri excepționale și a fost acceptată între autorii care contribuie la revista Nature. Această formulă stabilește relația dintre ciclurile solare de 11 ani și perioadele mai lungi de 370 de ani, care se manifestă prin așa numitele minime solare de mai lungă durată, în care clima Pământului devine mai rece. De ce este importantă această formulă matematică veți afla din interviul pregătit. Trebuie să mai menționez faptul că acceptarea unui articol în această revistă îi atribuie un grad maxim de relevanță științifică, acuratețe și este revizuit cu multă severitate. Desigur, aceasta nu înseamnă că revista Nature este un element absolut infailibil și fără greșeală, dar pe baza dovezilor ea acceptă corecturi și recunoaște erorile, publicând notele trimise de alți autori, pentru că nimeni nu e perfect și nimeni nu e un profet, iar adevărul absolut nu-l cunoaște nimeni. Înainte de a revedea partea întâi a acestui interviu, aș dori să-mi exprim nedumerirea legată de un fenomen social care se întâmplă pe mediile de socializare ale internetului, unde sunt prezent pentru a mediatiza emisiunile și totodată pentru a culege impresiile și sugestiile dumneavoastră. Ori de câte ori postez un grafic climatic, fotografii sau linkuri cu articole și filme video care au ca subiect fenomenele climatice, primesc două feluri de răspunsuri situate la două extreme aproape polar opuse. Prima categorie este cea a faptului că nu există nicio îndoială asupra faptului că singura manifestare climatică care se produce de peste 170 de ani este doar cunoscuta încălzire globală și care nu este una naturală, ci este în mod exclusiv și majoritar indusă de activitatea omului, fiindu-mi aduse mereu argumente că reprezentanții agențiilor guvernamentale au cercetători serioși și că nicio altă opinie nu este permisă. A doua categorie de păreri ale utilizatorilor de pe mediile de socializare se referă la infamul și neîndoielnicul proiect HARP de conspirații globale care au tehnologii secrete ce modifică clima și, prin urmare, orice fel de idee conform căreia modificările climatice din prezent, încălziri sau răciri, nu pot fi de sorginte naturală, ci ele sunt în mod obsesiv rezultatul acestor conspirații. Încerc să înțeleg de ce clima nu este și nu poate fi determinată de factorii naturali, măcar din întâmplare. Sunt și eu curios, oare nici măcar din întâmplare clima noastră nu poate fi determinată de factorii naturali? Ei bine, ori de câte ori postez o hartă oficială de pe site-uri climatologice acreditate, fără niciun comentariu personal, aceste două categorii de răspunsuri apar de fiecare dată. În mod special am lăsat în contextul unui alt interviu o opinie a profesorului Steven Pinker, care era legată de faptul că domnia sa este convins de influența factorului antropic, dar nu neagă existența factorilor naturali. De ce? Deoarece dânsul crede că un consens al celor câteva mii de membri ai IPCC, cercetători și mai ales consilieri guvernamentali pe probleme de mediu, au hotărât că doar factorul antropic este singurul factor care determină mersul climei înspre încălzire. Și am lăsat necenzurat răspunsul său, deoarece mi s-a reproșat de-a lungul timpului că nu se poate ca un jurnalist să nu prezinte toate punctele de vedere asupra unui anumit fenomen. Vizionați sau revizionați emisiunea și veți găsi punctul de vedere al profesorului Pinker, pe care eu îl respect și îl accept ca fiind în asentimentul acelor reprezentanți numeroși ai panelului interguvernamental. Dar haideți pentru o clipă să facem un exercițiu de logică și să trecem dincolo de voturi, de abțineri și îngrădiri. Și cu aceste gânduri de bună înțelegere și deschidere, de îngăduință și permeabilitate spre cunoaștere, vă invit să vizionăm partea întâi a acestui interviu foarte lung, dar am rugămintea să-l revedeți de mai multe ori de pe contul de Facebook al emisiunii pentru a putea asimila toate detaliile. Demonstrația este complexă, dar consecințele acesteia ne vor afecta viața în următorii 10-20 de ani. Dear Dr. Valentina Zarkova, welcome to our Science and Knowledge TV program on TVR Cluj, Romania for the first time.
Okay, thank you.
Because we meet for the first time, please tell us about your academic background and expertise.
I am a plant mathematician, solar physicist. I graduated from Kiev State University, Ukraine, did PhD in the main observatory of Ukraine in Gulesieva. I moved to the UK in 1992 to Glasgow, where I worked for 8 years and then become a permanent staff member at Bradford until 2013. And from 2013 until now, I work at the University of Northumbria, professor of mathematics. The University of Northumbria is Newcastle, north of England.
Our viewers already have some basics on climatology because we already discussed many issues in at least 9 hours previous interview with Professor Tim Ball from Canada. Starting from these basics, we are now entering into a new field of study which extends the climate changes understanding towards a new level, and that is the influence of the sun on Earth's climate and geology. We also have to warn our viewers that we are going to discuss very disturbing information, and they must watch this program several times after its premiere broadcasting on TV using the archive from my YouTube account. I thank you very much for accepting this special interview.
You're welcome. Although you have very nice solar astronomers in Romania, if you didn't know, in Bucharest there is a part of a solar group. You have Cristiana Dumitrace and Diana Besliu-Ionescu. They're also doing solar physics and some kind of solar activity. So after you did interview with me, you can speak to them. I know them personally. They're very good scientists. So they will give you more information about solar activity.
This is amazing, and I thank you very much. Can you also send me an email address?
Oh, they are in Bucharest Observatory. In the center of Bucharest, I can send you their emails and contact details later on offline. I will give you.
As part one of our program, we are going to discuss some history data, hypotheses, and scenarios. First, please tell us how sure can we be regarding the history of sunspot numbers observations 4 centuries ago, when at that time the telescopes did not have the magnification and precision which they have in our present days. Thus, many smaller sunspots could be missed.
Yeah, luckily the solar activity is not estimated by the total number of sunspots, but some average number of sunspots, averaged by different observatory, different observers, and taking into account the increased capacity of the modern telescope. So this is already been tackled by the scientists. Of course, they are aware that modern telescopes are more precise than in the ancient years, and most of the before 17th centuries, the sunspots were observed by Chinese astronomers and other astronomers in Europe using just visual observation. They project the sun on the wall and they see sunspots and they put the shapes, handwriting shapes around them. And then from these drawings, they measure sunspot area and then derive solar activity for this particular day. So all these mechanism and all these mechanism of observations and accuracy has been discussed numerously in number of different papers and meetings and so on. So people are aware. Only recently the accuracy of detection of sunspots was corrected, because using manual drawing of sunspot in the Karna Observatory, they overestimated the number of sunspots and used some slightly increased numbers. So this is ongoing task, and scientists are well aware of the problem, and it is being controlled. So it's been all the data being like measured or adopted to what has been seen before. So they're more or less coherent.
So can we trust those historical data?
We can trust our data more even than previous ones, because previous one, who knows, people were observing sporadically, not regularly. So we definitely can trust our data, because the sun is monitored with unprecedented accuracy and literally 24 hours, 7 days a week. So we now have much better, much more confident data about sun, and we can explore its features with much better accuracy.
No, I was referring to the historical period of time when little ice age occurred. Those data are still valid today?
Oh yeah, they're very good. There were, I think, the scientist Eddie Maunder, they explored this old data and then derived luckily the observations were done by that time mostly in Switzerland, Locarno and some other observatories. They were nicely processed and they're trusted, so they were definitely presented and analyzed in numeric papers, so we can trust them.
Okay, because it is very important on our next discussion. In climate science, many predictions are based upon historical data which are correlated with the present observation.
Well, we can trust them to some extent, keeping in mind that, of course, they were observed with very low precision instrument. Of course, they observed people who didn't know much about modern level of solar activity and physical processes and so on. So we can always have adjustment and put arguments forward saying they suggested in 18th centuries this and that, but now, knowing what we know now, we can say and so on. So we can always adjust, but we always refer to the accuracy people evaluated at that time. And this data are extremely valuable for us.
Thank you very much for clarifying this, and I'm happy those data are still reliable for our modern science and climate studies today. Now I'm going to the next question. Our Sun is the largest object in our solar system, and if we would calculate an average of its total radiant energy, the result is a relatively precise value, if we consider 100 years time frame. How much the sunspots add to this value, why human life on Earth depends actually on how much this sunspot adds a little more energy.
Sunspots do not add little more energy. They are like a reflection or catalyst of increase of solar activity. Let's first establish what are the sunspots. If you look at the tree growing in your garden, sunspots represent the root, where the tree is embedded into the earth. So the sunspots are root where magnetic loop, which comes on the surface, is embedded into the atmosphere of the sun, into the photosphere of the sun. So this is places where these loops are getting through the photosphere to the interior, where are the roots. These are the sunspots. So the sunspots are indications of a number of magnetic loops occurring on the sun. If you have a few sunspots, it means only a few loops on the sun. If you have many sunspots, there are many loops on the sun. Why are we so interested in these loops? Because all the activity happening in those loops. So the flare, when the loop started brightening, you see the flare. The flare comes and produces a lot of energetic particle, a lot of electromagnetic radiation, which travels to the sun and to the interplanetary space, toward the Earth and other planets, with solar energetic particle, with shock waves, with the other radiation, and they are the ones which increase the temperature. When you have flares, you have large flares, small flares, or mini flares, nano flares, they all heat the atmosphere. So these loops become very hot, like boiling water. If you have many loops on the surface and all the loops are heat, so your atmosphere become very hot. This is sun temperature increases, and this is the radiation from it increases toward the whole solar system. If you have less sunspot or less these loops, then obviously not much heating and not much radiation coming towards the Earth and other planets. Though we have to be very careful about the radiation, because the radiation variation between when the sun is in maximum activity and when sun in the minimum, it's just only a few percent. So the sun basically put the radiation very constantly, the same amount in watt per square meter per second, and it only varies when the sun is the minimum, just a few percent, 1%, and then when it was mountain minimum, it was decreased by 3%. This is maximum decrease you have. So whatever comes from the sun as emission is a very constant radiation. Irradiance of the sun nearly constant. It slightly varies when the sun is in a maximum or in the minimum. So obviously the main process of affecting the planet during solar activity are those energetic particles and various waves, coronal mass ejections, which are bombarding the planet's magnetospheres with energetic particles, with the shocks, and producing a lot of disturbances in geomagnetic space between the sun and the Earth and between the other planets. So the sunspots are just, catalysts. They show, right, if you have many sunspots, then activity must be growing. But they are not themselves producing any activity. They're very quiet guys. They're sitting like roots of the trees, sitting and holding those loops in the solar photosphere. So these are what the sunspots. Of course, if the sunspots, as I explained, you have many sunspots, it means you have many of those loops. And then if the very activity processes coming in those loops, the atmosphere becomes heated. If you have less sunspots, of course, you have less activity, the atmosphere cools off.
So the reality is that not those plus or minus 1% of the total energy of the sun...
Of radiation, of solar radiation, which comes the light. Solar light, this is a radiation.
Yes. So of solar radiation, solar light, this is the radiation, solar light, yes. So if it is not the plus or minus 1% of solar radiation, then what does regulate our climate? Are the particles which emanates from solar flares?
Well, this is what we assume and most people know, but it depends what people consider as the solar forcing in their model of terrestrial temperatures. So I cannot tell what they're considering, but most of them are considering all the solar radiance. They do not consider other energetic particles or magnetic field or other, and this is probably the deficiency of their models, why their models cannot predict real temperature variations, especially when you have a period of the prolonged solar minima like we're predicting, and at this time the irradiance will be reduced not that much, but the variations of the temperature would be much more dramatic. Therefore, in this sense, we can say, I can say that the particles and coronal mass ejections more affect the Earth and other planet magnetospheres than irradiance, because irradiance nearly steady, it slowly radiates, but these effects of these particles or coronal mass ejections or other disturbances actually is not considered in the models of terrestrial temperature. So this is the difference.
If we would consider a scenario whereby our sun would have no big sunspot at all, but the Earth would be orbiting just a little closer toward the sun, and the climate would be just perfect, then what would happen if suddenly the sun will manifest solar flares and sunspots?
It would be very dangerous.
Yes.
The closer we become to the sun, the stronger radiation becomes, and at the moment we are at the reasonable distance when our Earth's atmosphere can protect us from the harmful radiation of the sun. If we move closer, which means that our summers become hotter and winters become colder, it might cause very dangerous trend, might cause to the same variation what happened on Mars, that the life would disappear. So it would be very dangerous if the Earth moved much closer to the sun, even without flares. But if flare would occur, if we were closer and our atmosphere is adjusted to protect the power which comes after 1 astronomical unit. So whatever happens on the sun, its power obviously is decreasing with the distance. So some processes in the interplanetary space decreasing. So whatever arrives to our Earth, the magnetosphere, our magnetosphere is able to cope and consume and digest and process this radiation. If we move this everything closer and do not increase magnetic field of the Earth, very shortly, I believe, sun would burn out the Earth and the life would disappear, because we are at the moment at the right distance where we should be. So it's better we don't move the Earth.
Please explain what is happening on the surface of the sun when a sunspot emerges and how much this particular sunspot affects the climate. What is a duration of a sunspot? What is the duration of its effects on climate?
We don't speak yet about the effect of sunspot on climate. Let's say what are the sunspots. As we established, they are roots of the loop, which has two polarities. So because the loop has north and south, both roots of the loop are rooted into the photosphere. So how these loops come to the surface? They actually are formed by the solar dynamo mechanism, electromotive force at the solar interior bottom of the solar convective zone, and these loops appearing with following the dynamo mechanism. So dynamo of the sun, produced by dipole or quadrupole magnetic sources, produces these small loops which start traveling from the connective zone in the solar convective zone in the solar interior towards the surface. And normally it takes about 6 years, half cycle, to reach them to the surface. So the next solar cycle started forming in the middle of current cycle, and the next loops for the next solar cycle are formed at the bottom of convective zone, and they travel for number of these 5-6 years until they reach the surface. So it explains why the properties of solar interior are very important, because the number of loops are formed at the bottom is 1, but when they travel through the conductive media of the solar interior, which has its own property, the number of loops may be corrected, or the loop's properties are corrected. So whatever appears on the surface is the combination what happened at the bottom of convective zone when the loops are formed, and after they travel through the whole media of solar interior and appeared on the surface. So this is how dynamo mechanism works. So what we see on the surface, the product of these two processes, and we see them at the sunspots. And it explains now why sunspots are considered a proxy of the solar activity, because they are the root of those loops. So by counting number of sunspots and their polarity, we know how many loops manage to make their way from the bottom of convective zone to the surface. So if there are many of them, activity is increased and so on. When the activity moves into the minimum, the less and less of those loops manage to reach the surface. We see less and less sunspots. So this is very trivial, simple explanation. And the dynamo theory was introduced by Eugene Parker, 1955, and since then been developed by a brilliant cohort of scientists. And so this is well-known mechanism, not only formation and changes of activity on the sun, but in many other stars around in the galaxy, our galaxy and other galaxies. There are many suns around, which larger or smaller, which have similar activities to our sun.
Please explain the difference between sunspots and solar flares and protuberances.
Sunspot, we established this as the roots of the tree. Solar flares, you can call them, they are like flowers. When you have flourishing in the spring, suddenly you have nice period. You have a lot of flowers, and your trees, instead of being dark and boring, become nice, bright with green. So the only is different that trees, flowers, we know they occur in spring. In the sun, the flares occur not that predictable. We still don't know exactly. We cannot predict them necessarily within exact timing, but they are when these loops are brightening. So the loops appeared on the surface, boring loops with the same temperature, and suddenly they become very, very bright. And when they become very bright by some mechanism, this is when you see this like a flare, because you see this dark sunspot because the temperature is lower than photosphere, but suddenly between them you see this very, very bright spot, and you see that emission become much higher than the emission of the sun. And because you see this brightening, they call it flare. So if sunspots are dark, flares are white. They become very bright, and they're seen in many different range of electromagnetic radiation. So this is the difference between sunspot and flares. Flares occur very short time, up to 2 hours, start very dramatically, within a few seconds, increase radiation in hard X-ray, gamma rays, in UV emission, and all the spectral from high energy to optical and radio emission, everything shows emission during flares.
So they are
but before you go to the sunspot, from sunspot to flares, so before the flare occurs, it is like, what are the loops? We describe that they're trees, but they're trees with the branches, right? And because our loops have 2 roots, so the branches are connected to each other. They're like this one. And then very often, before the flare occurs, the branches have like a dip between them. And in this dip, you have very long plasmoid with a lower temperature, which calls protuberance. It's hanging on these branches and waiting until something happens. So when the flare starts, very often this magnetic field becomes reconstructing and pushes this prominence outside to the interplanetary space, causing filament eruption or causing coronal mass ejection and so on. So they're all related, but they're all different features in solar activity.
From all these kinds of manifestations explained earlier, the sunspots are the most relevant in regulating the climate, or all of them?
No, we can't say the sunspot most regulated and relevant. There are the nice proxies which are nice to be applied over the long period of time. The sunspots are very nicely linked to the general solar activity 11-year cycle or 22-year cycle. We only last 3 cycles we have catalogs of flares, H-alpha flares, or flares in high energy, X-ray flares, which we can compare what happened in the previous cycles. But this is only since Earth started exploring this space from early 70s and 80s. Before that, we didn't have flares, so we might be wanting to use flares as the proxies, but we can't propagate what happened 2 or 3 centuries ago, because at that time they didn't know what the flares. Carrington observed only 1800 first flare, so before they didn't have observation of flares. So this is why they stick. Maybe sunspots are not the best proxies of activity, but at least they're most reliable, because we can relate to them for a few hundred years backwards and compare how many sunspots were there, what was the activity, and so on. Now we have much more proxies, and this is why many people look into the proxies, some suggesting coronal holes to be good proxies, some suggesting CMEs, coronal mass ejection, good proxies. So we improving possible proxies of solar activities, but still benchmark anything we discover to the sunspots, because they're most reliable and most extended database for a few hundred years, for a few centuries, if you include the Chinese sunspot, maybe for a few millennia. So it will be reliable. So this is what we try to benchmark ourselves, what the ancient scientists thought, what happened in the past. And we only can benchmark it to sunspots because they were reliably observed. Other features were not observed. They're nicely observed last 3 solar cycles, but not others. So this is why, despite we made a huge progress, we still need to take into account what has been done in the past, because we want to benchmark ourselves towards the past.
Now we are arriving to one of the most important issues of this interview, which is the result of these correlations that you had just explained. And please let us both open your paper, Prediction of Solar Activity from Solar Background Magnetic Field Variations in Cycles. 21-23, page 4, figure 1, top plot. There are two curves having shifting color. How would we correlate those curves with the warm and colder climate? And why
we cannot correlate these curves because these two curves represent two different dynamo waves formed in the solar interior. One is formed at the bottom of the convective zone, and another is formed close to the surface. These are two waves in the solar interior which we do not yet relate to the climate. So we need to remember these are the waves, dynamo waves or magnetic waves inside the sun. Yeah, they are related. The summary curve of these waves, as we shown, it actually reflects the sunspot number. So if you look at this paper, we present that when we add these two curves together and produce the final summary curve, it actually reflects how many sunspots appear on the surface of the photosphere. And based on this curve, we can say, right, we have the curve describing the solar cycle. So when our curve has maximum, we have maximum solar activity. When solar curve comes to zero, it has minimal solar activity. So this is what basically our curve describes, coming from maximum to minimum solar activity and producing something like sunspot numbers. In one of the, I don't remember which, I think figure 3, we compared the summary, the modulus summary curve with sunspot number and found very good correlation. So if you reflect your summary curve only to the positive, make modulus, it very nicely fits the average sunspot numbers. So which tells us that background magnetic field of the sun actually the main force which allows this number of sunspots to appear on the surface. So remember the story, the sunspots are formed at the bottom of convecting zone and travel into the interior, which is electromagnetic media, and they've been somehow affected by this media, and the polarity of this magnetic field and the activity actually either suppresses whether this loop can appear on the surface or allow it to appear on the surface as sunspots. So what we did, it was early work in 2008, we found that the background magnetic field polarity and features are in anti-correlation with the magnetic field of sunspots, and this is also was found by German scientist Stix in 1976. So this what led us to the conclusion that if background magnetic field is the one which modulates appearance of sunspot, maybe we can play with the background magnetic field because we have the whole solar disk of this field versus a few sunspots. So my error bars, whatever we detect from background magnetic field, will be much lower than error bars of solar activity we detect with sunspot, because you correctly notice that, all right, there's very tiny sunspot and there are a few of them. It is very easy to make a mistake, isn't it?
I wish to ask you a very important question because time is running out very quickly. Please tell us about the possibility of a near future global cooling.
After we done comparison and discovered that the summary curve of these two curves, on the summary curve can explain nicely the occurrence of sunspots, we managed to actually derive the mathematical formula for this curve. So we applied some nice artificial intelligence method and derived that this curve can be explained by the series of 5 cosine functions. And after we derived this formula and fitted it to the curve, we now were in the power to calculate this curve forward and backwards. And this is what we did in the Nature paper. We calculated the summary curve 2,000 years or 1,200 years backwards. Yeah, we calculated 800, but in the next few years we calculated 3,000 years backwards and 1,000 forward. So when we calculated this summary curve, what we discovered, which was very surprising, that in addition to the 11-year cycles or 22-year cycles, if you include polarity of sunspots, there are another cycles, which we call grand cycles, with the duration 370, 400 years, which are repeating, give like a block of normal cycles. And when they come to the grand minima, we have minimum, very large minima in every 340 and 400 years. We call them grand minima. And this is the effect of interference, these two waves. Similar, we call it beating effect. It is well-known effect in the wave theory. When anyone tune in the piano at home, they put piano and put the fork, and they put the sound in both piano and fork, and hear how many beats they get in order to know how increase tension on the piano. So the same happened in the sun. The only thing that there's no one there who would tune the sun to remove the beat. So the sun showed these beats on the regular basis. So basically, reduction of these activities within 400 years is because these two waves, remember one wave at the bottom of the convective zone, one is close to the surface, they interfere with each other. And when they got in pure destructive interference, so they come in opposite phase, basically this wave cancel each other, and you have the minimal solar activity, similar like you have in Maunder minimum, or Wolf minimum, or Homer minimum during the Roman Empire. So these are the minima which we hit backwards to 3,000 years, and this we discovered, yes, indeed, this minima happened on a regular basis, and the Earth came through them very safely. Last grand minimum happened during the Maunder minimum. It was end of 17th, beginning of 18th century, 1645, 1715. It was the most prolonged grand minimum, about 6 solar cycles. When the solar activity is still there, you have max and min, but the amplitude is much lower. And because the waves are interfering, have destructive interference. But after we pass this period, the waves start again producing different phase. They become into constructive interference and produce a lot of solar activity and heat, which we observe in the previous 370 years since Maunder minimum.
Yes, but Professor Tim Ball said that before we will actually see the cooling, an intermediate time frame of few years, the phenomena will increase towards extreme. How much this will last, and when the actual cooling time frame should be expected?
Well, we seen the last winter, if you don't remember, we had snow here, very strong snow in December. In Northern America, there were blizzard. The flights could not fly. It was in December, then in March and April again. And the terrestrial temperature is decreased this year. So it started appearing. I agree with Dr. Ball that definitely the Earth is not like a soldier. The sun gave command, heat or cool. And the Earth said, yes, we cool and heat. No, we have all this water which needs to be rotated and turn around, and we exchange between water and Earth. So I trust possibly he is right, and the cooling will start. We predicted it start from this solar minimum. We thought will start from cycle 25, which is upon us. We at the moment approaching minimum between cycle 24 and 25. So the cooling will start now, and we observe it. It is cooler than it was last year. So it will be next few years. It will be cooler. Then we come to the maximum of solar activity. We probably would not see that much cooling during the maximum, and only in the next minimum between cycle 25 and 26, we might see very strong cooling, because this is where cycle 26 will reduce activity by 70%. So this is where the worst comes in 12 years, in 30s. In 30s, it will be really cold, and it will be really, so the Earth will be coming through this upcoming modern minimum for about 33 years, 3 solar cycles, but in different phases. And the most dangerous periods were the minima between the cycle. So we've seen minimum between 24, 26, we got this blizzard and late spring and so on. This will be next year, possibly another year. Then solar activity takes over. It will be like more or less normal until we come to the next minimum between cycle 25 and 26. And again, we will be seeing that, all right, magnetic field is reduced and decrease will be much worse. So this Earth system will have enough time to cool off and produce, temperature, or produce exchange between ocean and atmosphere and so on. So we will have this in observation for the next 20, 30 years.
So we still have about 10 years before the worst cooling will arrive?
Before the worst cooling will be, we have a little bit time when the sun comes through the maximum solar activity. Yeah, so we probably better learn what's happening now between cycle 24 and 25. It become cooler. So we expect it will be worse when cycle between 25 and 26, and prepare the nations for this worst period and prepare more heating, more food, because cooling is, when you have enough heating, cooling is not so bad. But the problem is with cooling if atmosphere is cooled, like we have now in Great Britain, because the winter we had snow in April and have wet fields, like potato crops are completely disappeared. They needed to replenish them end of April. So definitely we have harvest of potato much later and less than we would have normally. And similar will come with wheat, with other things. If you have wet, cold fields, they do not produce the same amount of crops which you expect. So if the winter become prolonged, probably the period during which the harvest allows wheat to get on other vegetables, fruit, will be shorter, and it needs to be checked it will be enough. Or we need to think about greenhouses to protect our crops and grow something independent of on the temperature. But this will be, it will not be like a constant. Luckily, we still have this maximum solar activity, which will warm up and produce more or less like normal life. It gives us time to prepare and understand what will happen next 10, 12 years and be ready for the next minimum between cycle 25 and 26.
And how much will last this worst cooling? 20 years? 30 years?
It will take about 3 solar cycles before the sun returns back to normal and start producing standard solar cycles with the increased activity. So it would take about 3 solar cycles. It is still less, twice less than it was during the minimum. So if we have cooling and snow, it will be not that dramatic as it was in the medieval ages. And given the fact that in Europe, most of the countries and most people survived this extended cooling period, mini ice period, without modern technologies and modern heating, we hope that humankind will survive the next grand minimum. The Earth came through millions of them, so it is not something unusual. It's standard, so it's survivable. You just need to be prepared and get ready to it.
You mentioned earlier the Milankovitch cycles. Please describe all the cycles of the sun activity and their duration in years, which are 11, 22, 68, 178 years, and so on. Please describe them all and what is happening with our climate when one or more of these are starting in the same time.
What will happen in the minimum. At that time, the grand minimum cycle converged with the 2000-year cycle, and the minimum was much longer, extended twice longer than the upcoming grand minimum. So it will be increased the extended effect, but given the history of the past, we have a few 100,000 years before any cataclysm would happen, so I wouldn't worry about it right now.
Așadar, aceasta a fost prima parte a interviului cu cercetătoarea Valentina Zarcova, de profesie astrofiziciană și matematiciană, care predă și cursuri la Universitatea Northumbria din Marea Britanie. Data viitoare vom continua prezentarea concluziilor foarte îngrijorătoare ale cercetărilor sale, care au șocat comunitatea științifică, domnia sa fiind somată de anumiți reprezentanți ai unor guverne și agenții climatice să-și retragă publicațiile. De ce s-a ajuns într-o asemenea situație și cine sunt cei care nu doresc ca asemenea informații să ajungă la publicul larg, veți afla în episodul al doilea. Așadar, nu-mi rămâne altceva de spus decât fiți alături de noi data viitoare la o nouă întâlnire cu știință și cunoaștere.